transformations can be categorized into two primary groups: horizontal changes and vertical changes. If we take this and we look at this function here, where you have e to the x, e raised to the 2x minus 4. My parent function is e to the x. So I'm looking at the inside of my function, which is going to be where x is located. That would be up inside the exponent. So anything that happens in there, we would consider a horizontal change. If we carry that out, the outside part of my functions change the vertical parts of my graph. Vertical stretches or shrinks or shifts up and down, or reflections vertically over the x-axis or another axis that's horizontal. Okay? And so you've got these two groups of changes. If we look at each part, let's just kind of go as it's written here. Let's talk about the outside. What does that negative sign do? It reflects over the x-axis. Now, a lot of people say, oh, this flips. Okay. In 9th grade, that was okay. You've moved way beyond that. If you say it reflects, okay, great, but you must tell me where it reflects. If it flips, I'd rather you not use the term flip. The correct vocabulary is it reflects. Okay, it reflects over it's a vertical reflection, right? It's going to flip vertically. So it's going to reflect over some horizontal line. In this case, it's going to make it reflect over the x-axis. And so I need to make sure that I know that, right? That's this piece right here. Let's go on to the next part. What about the 2? What is the 2 going to do to my Okay, it's a vertical stretch by a factor of 2. Okay, vertical stretches behave just like you think they would. If the number you're looking at is bigger than 1, it's stretching it by that number. If it's less than 1, it's going to shrink it. Let's be multiplying it by 1/2, so it's going to be half as tall as it was to start with. Okay? Just like you would think it would. What about the 6 on the outside? Good. And here I don't really need to be specific about the vertical or horizontal. If I say up 6, that's clearly vertical change. So it's implied in that. All right, what about the 2 on the inside? Here's the part where I'm thinking, you might not know this one. What would you say about this one? It is a horizontal shrink by a factor of 1/2. With that said, I'm going to put some notes up here that you may or may not know. So look at this. If you have e to the bx, we're talking about the coefficient of x. If b is less than 1, it's a horizontal stretch by 1 over b. So if I had to add 1/2 x, b to the 1/2 x, that would be a stretch by a factor of 2. Okay, just on the other side of that, okay, if b is greater than 1, then I would say it's a horizontal shrink by a factor of 1 over b. So it's backwards and upside down for you. So here, let me give you a way to do this first. If you were to take the number here, if you will take its reciprocal first, so instead of 2, we think about 1/2. Oh, 1/2 is less than 1. It's a horizontal shrink by 1/2. If you'll flip it first, it's easier to think about. Okay? Otherwise, if you don't know this, this is the part that I'm not so sure that everybody has done before. Okay? It is definitely not encouraged or not taught in when you first learn about these things. So definitely write that down. I'm going to ask you about things like this later on. It's not that you actually have to... You'll never graph things like this. You won't do it physically like that. It's just a matter of, I need to know what happens. It's important that you know this is a horizontal change. So if you don't know all this over on this side over here, make sure that you know that this happens Okay, it's just it's backwards from what you would think about the vertical stuff. So be careful about that. All right, and we finish it out. We know that minus 4 on the inside here, is going to be, this takes it to be right 4. I don't need to say horizontal shift right 4 because right is a horizontal movement. So, any questions about transformations? We good? All right, that was kind of review. Let's go back and talk about this. So what you see here is a traditional population growth formula. It's related to compound interest, but it's not the interest formula because you don't have an n involved. In this case, it's only compounding one time, and that's not optional. You can talk about population growth, population decay, bacteria growth, anything that relates to exponential growth or decay can be described using this formula. The compound interest formula is a little bit more complicated. We'll get into HalfLife, which is based on this formula as well. I'm going to put two equations on the screen. What I want you to do is I want you to tell me which one's growth, which one's decay. Okay, just write it down. Take a second or two. I told you something last, I guess it was Friday when we learned this first time. I said, based on this number, you can determine if something's growth or decay. So what in these equations actually allow me to say growth or decay? Which one? It's in the parentheses. It's this piece right here. Oh no. Which one of these is growth? Which one's decay? Growth. How do you know the top one's growth? It's bigger than 1. It's growing. Here it's less than 1. Shh. Decay. Okay, that's just something you need to be able to immediately, instantly realize. Okay. We good on that? Not really gonna, that's also just kind of background. Okay, on Friday we talked about exponential growth and decay, but more specifically we talked about graphing. I'll put this up there. We talked about graphing exponentials. Okay. So let me put a couple of problems on the screen. I want you to graph these two graphs. Okay, so the first one's going to be P of t equals 2 to the x. And I want you to graph the other one. Let's see. P of t equals 2 to the x minus 3. Just for practice, I want you to draw both of these graphs in the way that we did on Friday. The way that I encourage you to do this, I tried to teach you the most effective and efficient way to graph something with an exponential function. We're going to start off graphing the parent function because that gives me the foundation to graph. And on Friday I told you that if you're going to graph that parent function, it's going to be 1, it'll be 1/2, 1, and 2. In general, it was 1 over b, 1, and b. So it's the base of my function. In this case, that base is 2. So I'm going to go over here. I'm going to graph those parts. So we have -1 at 1/2, and 0, 1, and then 1, 2. So if you have that graph goes up like this, my asymptote falls in at y equals 0. In terms of the basics, that's about as basic as you can get for these graphs. I'm going to take that function. What kind of transformations happened right here? Here, it talks about shifting it to the right 3 times because it's -3. I love how my lag is so bad. There we go. So what does x or y change? X changes. And how am I going to change x? So I'm going to go ahead and I'm going to, right above this, I'm going to add 3 to all the x coordinates that I started with. Right? And so -1 plus 3 is 2. 0 plus 3 would be 3 and 4. I'm going to keep the same y values. So 1/2, 1, and 2. And so I'm going to go ahead and draw in my asymptote. It's always the same. I didn't shift up or down any. So I'm going to go over 1, 2, 3, and 4. So over at 2, 1/2.
Why'd you keep the same values for 1?
That transformation totally doesn't change the y values. I didn't shift it up or down any. Since I didn't shift up or down, then it just stayed in place. I literally cut it out and slid it over to the right 3 times. Let me draw the old one on this same graph. Right, so here's -1. So 1/2 was here. Then 1 was there. And look, Tolly. I simply did this.
Yeah, I got you. But if you worked it out, wouldn't so if you worked it out plug in 2 for
Try it. Try it. Get a calculator out. Plug in 2. If I plug it, let's do this one. If I plug in 3, 3 minus 3 is 0. What's 2 to the 0? 1. Let's plug in 0. What's 2 to the 0? 1. It still works out to be exactly the same. That's the nice part about it. And so really, what we did here, we simply took the x values and we plugged them in here and we shifted them down 3 times. Nothing else changed about the problem. Questions? Okay. This is some of the basic parts. Shh. Let's move on. Two problems here. This one's actually going to be an easy and a hard one. Can you write the equation? Shh. Can you write the equation of the problem that has a P0 of 12 and an R of 8%? Yeah, that's as easy as it sounds. Just write the equation out. The instructions were very simple. Simply create the equation to represent if I had an initial value of 12 and it's growing at 8%. I simply wanted you, I just wanted to see if you were listening, following instructions, paying attention. Apparently that's not the case. I simply asked you to plug it into the formula. Most of you didn't have any idea what I'd asked you to do. Catch up. Shh, listen. Listen. Don't talk about everything else in the world. You should focus on this. The next question is a little bit more involved. Shh. Listen. Shh. The next question is harder. Shh. You have 100 bacteria to start with. You want to know how long does it take to reach 350,000 if it doubles every hour. Shh. I'm going to give you 2 minutes. Go. Okay. We're going to go ahead and plug this into the equation. If you plug it in, it looks like this. Everyone in here should be able to get that. If it's doubling every hour, then it's listen, shh. Its growth factors, it's doubling. So the base of my exponent is going to be a 2. If I start off with 100, that's my initial value. If I want to see 350,000 at the end, then that's my result.
Why is it not 1 plus 2?
Because it is doubling. If I were to write it out, it's growing at 100% each hour. right? So it doubles, so it increases what it was before. So I would be doing 1 plus 1 to get 2. So it's growing at 100% an hour, or doubling its value every hour. So the question is, if you allow it to double every hour, how many hours would it take before you had 350,000 exactly? I know what some of you are thinking. Oh, this is going to be easy. It's plug and chug. Okay, listen. You just start plugging in numbers. You're trying to get 350,000. Shh. These answers will not be nice. They will be decimals. I will not give partial credit for a guess and check solution method. It says that you did, now multiple choice, that's multiple choice. I will not give credit for guessing and checking because you are not using the skills I'm teaching you right now. So pay attention and watch. In order to solve an exponential equation, like this one, okay, I have to convert this into its logarithmic form. Now, so let's go ahead. Is there something I can do here first before I solve it? I want to divide by 100. I need to get rid of it, so I need to do everything I can before I switch it over. So let's go ahead and divide by 100. Shh. Listen. And so 3,500 equals 2 to the t. Whenever you have, and this is the important part, whenever you have a scenario like this where your variable is in the exponent, I don't have any options, at least in this problem. I'm going to have to convert that to a log unless I can get both sides to be 2 to some power. And 3,500 is not a power of 2. Okay? So, here's the key step. What I remember is that 2 is the base of my exponent. All right, I'm going to write something in the top part of the screen there that I remember when I go to convert from logs to exponents. This is the conversion, or these are the two things that I memorized. If I have this down, a lot of you remember this from last year. If I have this down, then switching between the two, it's not a big deal. We all will agree that 2 cubed is 8. Right? Its logarithmic form, its counterpart, looks like this. It's log base 2. And when you do, since the bases are exactly the same, base of 2 for the exponent, base of 2 for the log, the logarithm, the answer to a log is always an exponent. So I can say that's equal to 3 because that's the exponent for 2. So the 8 would go here. If you can remember that, then converting from log to exponent is not really a big deal. So let me go ahead and finish out this part. I'm going to take the log base 2 of both sides. Took the log of one side, says log base 2 of 3,500, log base 2 of 2 to the t. There's a real important rule that I have to remember, especially when I'm looking at this side over here, right? What is it about this that I need to remember? If I have a base of 2 and I have the base of my exponent is also 2, what happens? They cancel out. Okay, and so that becomes log base 2 of 3,500 equals just t. And so at that point, what I can take this next step is type that in my calculator. Now, some of you can do log change bases in your calculator, which is really great. If you have a TI-84, a newer one, if you've updated it, it will do a change of base. If you have an older calculator, then you may not be able to do that, which is fine. Shh, listen. Here's the change of base formula for anybody on any calculator to do. It's log of the big number, log of 3,500, divided by a log of the base. So log of 2, right? So it would look like this. Everybody has a log button on the calculator, so find that button. It's just log with no base at all. Okay? L-O-G. Okay? So find that calculator.
I'll figure it out. I'll figure it out.
Push comes to shove, you can just do log 3,500 divided by log of 2. Notice, listen. Notice that these logs that I'm writing on the right here in this fraction have no bases written down. We call this the common log because it's base 10. On your calculator, you have the log button. Everybody has it. Okay? It's there. Log button. It's always a base 10. Everybody double check, type this in your calculator, and see if you can get that result to come up. You should get 11.77 as the solution, which rounds to 11.8. Okay? Some of you can do the log base change formula. And so if you can, it makes this out to be really nice.
Oh.
Okay.
It makes me type it in as a natural log and then.
Wait, are we gonna not do example 2 or can we not solve example 2?
That was example.
No, it wasn't. That was example 3.
Yes, it was. Let's talk about this one and we'll come back. Shh. Gentlemen. HalfLife. HalfLife is just another exponential equation, except it's a exponential decay type of problem. In this case, we have a formula, and you might want to write this down because it's not really written anywhere in your book or anything. HalfLife. Now, this may be different from what you see in your science classes. This is coming at it purely from a exponential functions type of description. All right, HalfLife. P0 is the amount that you start with. Shh. Since this is a half-life, where our growth factor is by 1/2. That's why we see 1/2 in the equation. Okay, at this point, T in this problem represents the amount of time that's passed. Our HL is the half-life. This can be in days, it can be hours or seconds or years or millennia. It doesn't matter. But whatever the half-life is in terms of time, your T will also be in that same amount of time. So let's do this. I want you to tell me if you have a half-life of 20 days and I have 5 grams of a radioactive substance, I want to know how many days do I have to wait in order for that substance to be down to just 1 gram. Take a few minutes and work that out. One of the first things that you have to be able to do in these types of problems is just take the information that's given to you and pull the right formula out, plug in that number, those numbers, and see how it works, right? And so we're going to plug that in. Everybody in this room should be able to get here. Okay? 5, listen. 5 is the initial value, right? That's right there. Initial value is 5. The final value should be 1. And the half-life is 20. I did nothing but here's the formula. Here are my numbers. Let's plug them in. Questions? Okay, step 2. Are there any basic operations that I can do before I take the logs? I need to divide by 5. Shh. If I divide by 5...
Oh, dang it.
You wrote it in your exam.
Okay. Shh. You go ahead and just write this all the way out so you can see it. Shh. Okay. And so we have the 5's cancel. We have 1/2 to the T over 20 equals 1/5. Shh. Because I have a base of 1/2, I'm going to have to take the log of both sides using a 0.5 base. It cancels on one side, leaving me with T over 20. And I have log base 1/2 of 1/5. I can type that in. It's log 1/5 divided by log 1/2. Or if you have the ability to change your base, then you'll just type it in like it looks. What would I do after this? We all know what to do. Oh, no. In fact, you're going to tell us what to do. What are we going to do?
I don't know how you get to t over 20 equals 1.5.
Shh,
That's the part that
let's back up. We're getting there. Shh. Go back here. Shh. Okay, the first thing I did was I simply divided both sides by 5, and I got this part. When you go to the log step, you have to look at your exponent. Okay, whatever the base of the exponent, because the exponent is where my variable is. That's where t is. So I need to use a logarithm with a base that is the same exact base as my exponent. So we have to take log base 1/2, because it's going to cancel out, leaving me with just the exponent. Right? And so if we come up, I'm going to write this on the top. If you simplify that, you're going to get t equals 20 times log base 1/2 of 1/5. And that's equal to, was it 46 point something? What'd you get? 46 point what? 46.4. So I would expect it to take 46.4 days for that to happen. It's real important to go through these processes instead of just copying them down. Shh. I'm going to explain it. Let me go one more step, and I'll explain it. There's your homework.